All right, welcome back to the deep dive. Today we're diving into a paper that's generating quite a bit of buzz. It's Deep Learning is Not So Mysterious or Different by Andrew Gordon Wilson. And essentially it's taking aim at this idea that deep learning's generalization capabilities are, completely unique or even anomalous.
Yeah.
We're talking about, things like benign overfitting, double descent.
Mm-hmm.
The paper is arguing that these behaviors, they can actually be explained by existing generalization frameworks, specifically frameworks like PAC-Bayes and Countable hypothesis bounds, particularly when you factor in this concept of soft inductive biases.
Right. And for our listeners who might just be catching the short form edit of this, the big takeaway here is that deep learning's generalization, this thing that sort of captivated the field, it might not be as revolutionary or as different as we initially thought. There's a good chance that these well-established theories, they actually hold a lot more explanatory power than we've maybe given them credit for, especially in the context of these, seemingly strange phenomena that we see in deep learning.
If you're in the AI research world, ML engineering, you've probably heard this narrative that deep learning operates on a different set of rules than, classical machine learning.
Yeah.
This deep dive, this is really going to challenge that head on. We're going to be going deep into Wilson's arguments, looking at the evidence he presents. And then what we really want to do is connect these ideas back to simpler models as well.
Yeah.
Things like linear regression, polynomials.
Mm-hmm.
Because ultimately, we want to give you, our technically minded listeners, the insights that you can actually take away and use to better understand the research that's coming out, even the research that you yourselves are doing.
Absolutely.
So to kick things off, let's really get to the heart of this paper. It seems to be saying, hold on a second, deep learning's generalization. It's not like rewriting the fundamental rules of learning.
That's the core message, yeah.
Yeah.
There's this common perception out there, especially when you start talking about things like over-parameterization.
Right.
Where models have way more parameters than data points.
Yeah.
And then you have these models that can perfectly fit noisy data, but somehow still generalize well, which is this whole benign overfitting thing.
Right.
And then, of course, you have the double descent curve, which is still kind of baffling to a lot of people.
Yeah.
Test error goes down, then it goes up, and then it goes down again as the model gets more complex.
Yeah.
These sorts of things, they've led a lot of people to think, okay, our traditional generalization theory, it just doesn't apply to deep learning.
Yeah.
We need something entirely new.
Right.
And that's precisely what this paper is pushing back against.
Yeah, so they're saying these aren't like deep learning specific quirks, that these are actually more fundamental.
These behaviors, they're not some kind of mysterious phenomena that are only found in neural networks. And in fact, the paper goes to great lengths to show how you can observe these exact same phenomena in much simpler models.
Yeah.
Even linear regression, like figure 1 in the paper, has these really striking examples of both benign overfitting and double descent happening with, the simplest model you can think of, a linear model.
Linear model showing benign overfitting and double descent. That's kind of mind-bending when you consider how often those are framed as these deep learning specific problems that we need new theory to explain.
Exactly.
It's like, wait a minute, maybe we don't need to throw out everything we know.
And that's what's so interesting here. The emphasis is on how these frameworks that we've had for a while,
right.
PAC-Bayes, countable hypothesis bounds, they actually have the tools to account for what we're seeing.
Right.
It's not that our understanding of generalization was wrong, it's maybe that we haven't fully appreciated how these tools apply to deep learning.
Okay, so let's talk about this idea of soft inductive biases. The paper spends a lot of time on this, moving away from this idea of hard restriction biases in the model's architecture. So what are soft biases and how do they contrast with these, more traditional architectural constraints?
Right. So the traditional view of inductive biases is that you're essentially hardwiring constraints into the model's architecture itself. Like with CNNs, convolutional neural networks, a classic example.
Right.
The architecture forces this locality and translation equivariance through things like weight sharing and pooling. That's a restriction bias. It's fundamentally limiting what kinds of functions the model can learn.
Right. It's saying the model must have this specific structure, these specific properties.
Exactly. Soft inductive biases, they take a different approach. They allow for a much broader, a much more flexible set of possible functions that the model can represent. But within that large space, they introduce a kind of preference.
Yeah.
They nudge the model towards certain types of solutions without explicitly ruling anything out. So it's like guiding the learning process gently towards solutions that are more likely to generalize well.
Yeah.
Often, these are simpler solutions, but it's not a hard constraint. Figure 3 in the paper, it's a really nice visual of this.
So it's not about what the model can't do, it's more about what it's statistically encouraged to do.
Yeah.
Could you give an example of how these soft biases actually show up in practice?
Sure. So one example the paper talks about is order-dependent regularization in polynomial regression. So instead of saying, okay, we're only going to use a low-order polynomial to prevent overfitting, which would be that restriction bias, we could use a high-order polynomial, which gives us a lot of flexibility.
Right.
But then we apply a penalty that basically says, hey, the higher the order of the coefficient, the more you're going to be penalized.
Right.
So it's creating this soft bias towards simpler, lower-order functions unless the data really requires that complexity.
So the model can be complex, it has that capacity, but it's incentivized to stay simple if it can get away with it.
Yeah.
And the paper even gives like a very specific form for this loss function, right? Something like loss equals data fit plus the sum of gamma to the JWJ squared, where gamma is greater than 1. Is that right?
Yes. That captures it perfectly. The first part of that equation is saying, hey, you want to fit the training data well. But then that second term, the regularization penalty, that's where the soft bias comes in. That gamma being greater than 1, it's exponentially increasing the cost as you go to higher order coefficients. So it's really pushing the model towards simpler solutions when they're sufficient. And you can actually see this in action in figure 5, where they show how this regularized high order polynomial can work really well across different data sets, even when the complexity and size of the data varies quite a bit.
And these soft biases, they aren't limited to just this polynomial example.
Right.
The paper also talks about things like Bayesian priors and these residual pathway priors, the RPPs, for soft equivariance.
Exactly. So Bayesian priors, they can encode this prior belief that certain parameter values or function classes are more plausible than others, which acts as a kind of soft regularization. And then with the RPPs, those are a way to soften those hard architectural constraints we talked about. Like if you wanted to enforce strict equivariance in a CNN, you could use RPPs instead to say, okay, I prefer equivariant behavior, but I don't need it to be absolutely perfect at every layer. And what's really interesting is the paper mentions this finding that transformers, after they've been trained on a massive data set, they can actually show even stronger translation equivariance than CNNs, which suggests that they've learned this kind of soft bias for compression that's related to symmetry.
Okay, so soft inductive biases, they create these preferences. But how do the generalization frameworks, the PAC-Bayes and the countable hypothesis bounds that the paper really leans on, how do those actually tell us why this leads to good generalization and explain those weird phenomena we started with?
So these frameworks, they offer a different way of thinking about generalization. They shift the focus away from how big your hypothesis space is, and instead they look at how likely individual hypotheses are or distributions over them. Let's start with the countable hypothesis bound. It's theorem 3.1 in the paper. It says the risk of a hypothesis, R of H, is less than or equal to the empirical risk you see on your training data, R hat of H, plus this penalty term. And that penalty term, it depends on how likely your hypothesis was before you even saw the data. So hypotheses with a higher prior probability, they get a tighter, a more favorable bound.
So even in a massive model with tons of parameters, if your learning process, which is guided by these soft biases, tends to favor certain simpler explanations, those explanations are inherently going to be more likely, right? Higher P of H.
Exactly. And the paper connects this to Kolmogorov Complexity, K of H given A. It's basically the length of the shortest computer program you'd need to describe your hypothesis given your model architecture. So simpler models in that sense, ones with shorter descriptions, they have lower Kolmogorov complexity. And that means a higher Solomonoff prior, which gets plugged into the bound. So the more compressible your model is, the shorter that program needs to be, the better its generalization is going to be, even if it fits the training data perfectly. Figure 2 really illustrates this. Expected risk is less than or equal to empirical risk plus model compressibility.
That's a really intuitive way to put it. Now, what about PAC-Bayes? How does that fit into all of this?
So PAC-Bayes takes it a step further. Instead of just looking at one single hypothesis, it considers a whole distribution of desirable solutions. And it uses this thing called the Kullback-Leibler divergence, or KL divergence, to measure how different that distribution is from your prior distribution. This leads to even more nuanced bounds. And importantly, these bounds can hold even for models with billions of parameters, as long as there's this strong preference for certain types of solutions encoded in the prior. And this isn't just theoretical. The paper mentions that these PAC-Bayes ideas are now being used to analyze LLMs, large language models.
It's really interesting that the paper has this whole appendix dedicated to addressing misconceptions about PAC-Bayes, like people thinking it only applies to stochastic networks, or that the bounds always get worse as models get bigger.
Right. It's important to clear that up. PAC-Bayes can be applied to deterministic networks, and the bounds can actually get better with bigger models if the compression bias is strong enough. The key point is that these frameworks give us a way to formally understand how a neural network, even a super complex one, can still be considered simple in this Kolmogorov sense, or in terms of the prior distribution over its parameters.
Okay, let's bring this back to those weird phenomena we talked about earlier. How do these frameworks help us make sense of benign overfitting, where models fit noisy data perfectly, but somehow still generalize well?
So benign overfitting, at first glance, it really seems to contradict classical generalization theory. You'd expect terrible performance when you fit the noise, but the paper says it's not this deep learning mystery that everyone thinks it is. The intuition is that you have this flexible model, a loss function, that really pushes it to fit everything, even the noise, and then this underlying bias towards simpler solutions within all the solutions that fit perfectly. That polynomial example we talked about, that's a great illustration.
Right. The high-order polynomial has the power to fit the noise, but the regularization nudges it towards smoother, simpler functions if there's a clear structure to the data.
Exactly. And more formally, PAC-Bayes and countable hypothesis bounds, they can give you guarantees even in situations where you have benign overfitting. The paper talks about reproducing those noisy label experiments, originally done with neural networks, using Gaussian processes. And what they found is that the marginal likelihood, which ties into PAC-Bayes, it decreases as more labels are randomized, meaning the framework is sensitive to the structure of the data. You can tell the difference between learning from real structured data and learning from random noise.
Okay, so what about overparameterization? We've got these models with way more parameters and data points, and they're doing incredibly well. How does the paper explain that?
So the paper basically says we shouldn't be surprised that over-parameterized models can generalize well. In fact, in some areas of machine learning, like Bayesian nonparametrics, people have known about the benefits of having a huge model capacity for a while now. The key is that having more parameters can both give you the flexibility to fit complex functions and, kind of counterintuitively, it can make the bias towards simpler, generalizable solutions stronger.
Wait, a stronger bias with more parameters? That seems kind of backwards.
It does, but research has shown that larger models, after training, they can actually have a lower effective number of parameters. This means that even though you have a ton of parameters, the model might only really be using a smaller subset of them. Plus, there's evidence that larger language models have a stronger bias towards producing things with low Kolmogorov complexity. The idea is that overparameterized models have a lot of flat minima in their loss landscape, these regions where you can change the parameters a lot without changing the loss much. And these flat minima, they tend to be associated with more robust and generalizable solutions. Figure 6 in the paper shows how this can work, how bigger models can actually lead to a stronger bias for simple functions.
That's pretty wild. So it's not just about the optimization algorithm, it's about the structure of the model itself.
Exactly. And the paper even suggests that stochastic gradient descent, SGD, might not be as important for generalization as people think. They point to cases where full batch gradient descent and even random guessing can lead to good generalization in these overparameterized regimes.
So SGD might be helpful, but it might not be the magic ingredient everyone thinks it is.
Right.
Okay, let's talk about the last one of these phenomena, double descent. That weird U-shaped curve where the test error goes down, then up, then down again as you increase model complexity. The paper is saying this isn't some new thing that deep learning discovered, right?
That's right. Double descent has actually been observed in all sorts of models going back to the 80s and 90s. It's not unique to deep learning at all. People have seen it in random forests, random feature models, even linear models. The explanation usually involves this idea that as you increase model capacity, you first get better at fitting the data, then you start to overfit. But then as you push into this really over-parameterized regime, something interesting happens. You start to see the second descent, where the error goes down again. And that's because in this regime, you're basically creating more and more of those flat, compressible solutions we talked about, and the effective number of parameters is actually going down. The paper uses a simple linear model example to illustrate this, where you have more features than data points. As you keep adding more features, the signal kind of gets spread out, which reduces the complexity of the solution you learn. Now, what's really cool is that PAC-Bayes bounds can actually track this double descent behavior.
So across all these seemingly mysterious things that people have attributed to deep learning, this paper is basically saying, hold on, we already have frameworks that can explain a lot of this. It's about soft inductive biases, compressibility, and these ideas from PAC-Bayes and countable hypothesis bounds. But if those aren't what make deep learning special, what does the paper say are the truly distinct things about it?
The paper really focuses on that in Section 8, and the first thing it points to is representation learning. Unlike a lot of traditional models that use fixed basis functions, things like polynomials or radial basis functions, neural networks learn their basis functions from the data.
So it's not just about fitting the data with a set of tools you're given. It's about learning the best tools for the job as you go.
Exactly. And that's super important when you're dealing with these high-dimensional, complex signals that we see in the real world. Fixed similarity metrics, they often just don't cut it. Representation learning lets neural networks come up with these task-specific notions of similarity, which is crucial for doing things like extrapolation, making predictions on data that's really different from what the model was trained on. They use the example of predicting face orientation, where simple pixel-wise distances aren't going to tell you much, but a deep network can learn these internal representations that capture the underlying geometry.
Right, so it's figuring out the right way to represent the data to solve the task. What else does the paper highlight as a distinct aspect of deep learning?
The next big thing is universal learning, especially in the context of transformers and their ability to do in-context learning.
Yeah, we've gone from these specialized models designed for very specific tasks to these more general-purpose models that can do well across a wide range of domains.
Exactly, and the paper suggests that this is connected to this idea of low Kolmogorov complexity again. Both neural networks and the way data is distributed in the real world seem to favor solutions that can be described concisely. This universality is especially apparent in these large pre-trained transformer models. They can do surprisingly well on tasks they've never seen before, even in zero-shot settings. It's like they're learning these fundamental principles during pre-training that they can then apply to new situations.
That's a really fascinating idea. It's like they're building up this internal model of the world that they can then adapt to specific tasks.
Right. The paper uses this analogy of a mixture of Gaussian process experts. It's like the transformer is implicitly choosing the right combination of kernels based on the context of the task.
Okay, so representation learning, universal learning. What's the third thing the paper points to as a relatively distinct aspect of deep learning?
The third thing is mode connectivity. This is a pretty surprising phenomenon that's been observed in the loss landscapes of these deep networks. So imagine you train the same model multiple times with different random initializations. You're going to find different local minima in that high-dimensional parameter space. But it turns out these seemingly isolated minima are actually connected by paths where the loss doesn't increase very much.
So it's not like these models are getting stuck in totally separate valleys.
Exactly. They're all part of this connected landscape. And that's a big deal because it challenges this idea that these loss landscapes are super rugged and disconnected, with huge barriers between good solutions.
All these different well-performing models are actually in the same neighborhood.
That's the idea. And this has led to new optimization techniques like stochastic weight averaging, where you average the parameters from different models, and it can actually lead to better performance. This mode connectivity thing, it's not unique to deep learning, but it seems to be much more pronounced in these models.
Okay, so to recap, this paper by Andrew Gordon Wilson is basically saying a lot of what we thought was mysterious about deep learning isn't actually that mysterious. We have the tools to understand things like benign overfitting, overparameterization, and double descent. It comes down to soft biases, compressibility, and these frameworks like PAC-Bayes and countable hypothesis bounds.
Absolutely. And I think it's a good reminder that we should be looking for connections between different areas of machine learning, and that a lot of the foundational ideas we need, they were developed before deep learning even came around.
Right, we're not starting from scratch here. Now, for our listeners out there, here's something to think about. If compressibility is so important for generalization, what kind of new architectures or training methods could we come up with that really exploit this? Could we build models that are inherently biased towards low Kolmogorov complexity?
That's a great question, and it could lead to some really exciting breakthroughs in areas where deep learning is still struggling.
And to everyone listening, we've only scratched the surface of this paper. There's a ton more in there, including discussions of common misconceptions about PAC-Bayes and a lot of references to other work in this area. Definitely check out the paper itself and do some exploring.
Agreed. It's a really thought-provoking paper.
All right, that's it for this deep dive. Thanks for joining us, and we'll catch you next time.